One of the simplest way to have oscillations of an object is hang it with a thread and tie the other end of the thread at some place and just pull this object and leave it. So, that is how simple pendulum oscillates. In simple pendulum, you have a thread and then a mass, and this end of the thread is fixed. You pull this mass on one side and leave, and it oscillates. So, at a certain time, if it is here and if this angle is theta, then it will, and you leave it from here, then it goes like this and comes like this. So, it oscillates on an arc of this circle. How do we get the expressions for time period? We write equations of motion. If you take angular position as your variable, then you have force mg, and here is the axis of rotation. So, you take torque about that, and that will be mg into L into sin theta. That is the torque of this mg, and it will try to decrease this theta here. So, this is mg L sin theta in the opposite direction, and that should be equal to I alpha, and I will be, moment of inertia will be mass times length square. Remember, here is the axis of rotation. So, this distance is L. So, it is ml square times d2 theta dt square. And then you say that theta is small, so sin theta can be written as theta, and then it is d2 theta dt square is equal to minus g by L theta, and hence omega is square root of g by L. And if you need time period, it is 2 pi by omega, and that is 2 pi square root L by g, the standard equation, the standard formula for time period of a simple pendulum that one studies in schools. Now, it is always said that you oscillate the pendulum with small amplitude, and most of the textbook says that your amplitude should be within 4 degrees. What is so special about 4 degrees I cannot say, but that is the kind of number it is mentioned, and that comes from this approximation. In place of sin theta, we are writing theta, and then you get this expression, and this will be better and better if this theta is small, because sin theta, sin theta you can expand as theta minus theta cube over 3 factorial and so on. So, if you are writing sin theta equal to theta, that means you are neglecting this theta cube in front of theta, or you are neglecting theta square by 6 in front of 1. So, that is the place where this approximation is needed, and that is why this formula is valid for small amplitudes. But if I exceed that 4 degree limit, if I go for 10 degrees, 15 degrees, 20 degrees, how much will be the difference? So, let us measure it with a simple pendulum, which is not that simple in fact, and see how much is the difference if I increase the theta, this amplitude much beyond that 4 degrees or 5 degrees limit that textbooks say. So, let us look at this pendulum. So, here I have this pendulum, a thread is here, and from this thread a ball is hanging, is the same ball with which children play in lanes, cricket and all other games. And to measure the time period, we can use a stopwatch. So, I will be using this mobile stopwatch to measure time of say 10 oscillations. So let me first oscillate with small amplitude. So when it comes to this side, I will start the stopwatch. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So in 10 oscillations, it took 12.6 seconds. Small amplitude, oscillations, and it took 12.7 seconds, 12.6 seconds. Now let me oscillate it with a large amplitude. So I am pulling it to a large angle. This angle, although I am not measuring, but must be more than 45 degrees, and I will leave it from here. Once again, here it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13 seconds, 13.0 seconds. So large amplitude, ten oscillations, 13.0 second. But you don't have to believe this data, because starting the stopwatch, stopping the stopwatch right at the time when this ball is extreme, that synchronization, all these things may involve errors, and those errors are typically of the order of 0.1, 0.2 seconds. So essentially you should do several measurements, 3-4 measurements at least, and see if there is a variation, and there will be variation if you do the experiment, and then take the average value. If the variation is very large, then you have to improve your experimental skills. But if the variation is within 0.1, 0.2 seconds, then you can take average value 3, 4, 5 readings, and then you can get what is the time period for small amplitudes, what is the time period for larger amplitudes. You can perform this experiment as a function of amplitude, how it changes and all that. So if you do a proper mathematical analysis without making this approximation that sin theta is same as theta, you can get an expression for time period which is a better presentation. And if you do this analysis, solve this differential equation, what you get is your time period is something like t equals t naught, which is this, and times 1 plus alpha square by 16, and then higher powers. So if you take alpha equal to 1, and what is that alpha? Alpha is the amplitude, this amplitude. So alpha is 1 radian, and 1 radian, you know how many, it's 180 degrees is pi radian. So if you take this as 3.14 radian or so, 1 radian means 180 degrees divided by 3.14, so something like 57 degrees. So at alpha equal to 1, it is a huge amplitude, 57 degrees of amplitude, and even then this will be 1 by 16. 1 by 16 is 6% of error, and later terms will be even more smaller. So that is how the amplitude variation, time period variation with amplitude takes place. Now it will be your task to construct a simple pendulum and measure the time period for different amplitudes and see that how it varies and whether it agrees with this or you need even more terms. Now to start a pendulum itself is a very skillful job. If you think that I just pull it and leave it, see what happens. If I just pull it and leave it, see what kind of jerky motion it starts with. So one of the efficient ways is that you take some kind of a textbook or a notebook and then push this ball to whatever amplitude you want, and then move this notebook rapidly in the opposite direction and see how smoothly it goes. So the idea is that when we release it, it should have V equal to 0, theta is equal to the amplitude, and then it should start with V equal to 0. And for that you do not have to apply any force on this, so gently remove this so that this contact is broken. And it goes in a much smoother path. So we have always assumed that this ball moves in a vertical plane. So it is just a two-dimensional motion. We do not think that it goes in transverse direction, and that is perfect. If my initial conditions are initial displacement is in this vertical plane, and if the velocity is 0, then sure it will go in this direction because there is no force on the transverse direction. So what happens if I give it an initial transverse velocity? Then it has to move in this plane, and what do you expect? You have in general a motion in this plane, at the same time there will be displacement in the transverse direction, so it should be some kind of an ellipse, and it is an ellipse to start with, but then you watch how the motion changes with time. So I am releasing it, but not with 0 velocity, a slight push on the other side. It will make a jerk, but ignore that. Can you see how that ellipse is rotating? When I started, what was the mean plane of motion and what is the mean plane of motion now? Watch it again. I start from here and see it is going mostly in this plane, and now it is going in this plane mostly, roughly. The plane is changing or that ellipse is rotating. So I had started, that time it was going like this, and later on it went like this. So the ellipse rotated in this direction. If I give the transverse velocity towards myself, see what happens. See how the plane is changing, how the ellipse is rotating. Where is the major axis? It is now rotating in the opposite direction. Once again, I'll give it slight velocity towards myself. Mostly it is like this at this instant, and now it's going. The plane is changing. The ellipse itself is rotating. Okay, so the mathematics of this is a little more involved, which I will not be indicating even, but if you are interested, you can get this in this particular book. It is Mechanics or Principles of Mechanics something by the authors Sinjay and Griffiths. I told you that if I start the pendulum with the initial condition theta equal to some theta naught and v equal to 0, it goes in its original plane, and if I give a transverse velocity, then it goes in some kind of an ellipse which also advances, which also rotates. But now what I am going to show you, I will release it with 0 velocity, and you watch if any change in the plane of motion takes place. So I will do 3 experiments, and you carefully and patiently watch about the plane of its oscillation. So first is when I am displacing it parallel to this plane made by this rod here, this is stand, and this thread in equilibrium position. So this is the reference plane, you can say, and in this plane itself I am displacing it, and I will release it. Watch for some time and see if any change in the plane of motion is noticeable. It oscillates in the same plane in which it is started. That is expected, that is understandable. We did not give any velocity to start with, and therefore the torque of gravity is just oscillating it in that same plane. Let me stop it and displace it in the perpendicular plane. So you have a vertical plane made by this rod and this thread in equilibrium position. Perpendicular to that, I will displace it and see what happens. You have to give it some time. So far it is going in the same plane in which I started it. Continues in that plane. As expected, there was no initial velocity. So no reason to make any displacement in the perpendicular direction. it goes like this. Now in the third case, I will pull it in a direction making some 45 degree type angle with that plane, and then let us see what happens. So I am taking it in some inclined direction like this and releasing. Indeed, I released it with v equal to 0. Initial velocity, I have not given any transverse velocity. See, it has picked up transverse velocity on its own. Now it's almost rotating in the plane which was initially thread, and this rod was making this vertical plane. It's almost rotating in that plane, the original vertical plane made by the thread and the rod. So, why did it change the plane? When I release it with 0 velocity, it should continue in that same vertical plane, but it doesn't. At the same time, if my initial displacement is in one particular direction, it continues in one plane. If initial direction is perpendicular to that, it again continues in the same plane. But if the initial direction is somewhere else, then it starts changing the plane of rotation. So where is that extra force coming in? Where from the transverse force is coming in? That is coming in by this knot that we have put here. It's not a point contact as such. This point is really not fixed. What we have done, we have wrapped this thread 3-4 times and then put a knot here. And at the knot there is some structure, some triangular structure. And when this oscillates, that triangular structure gets deformed. And from there extra forces come, and that changes the plane of motion.